the next speaker is Katherina von Dichter from Germany. Please, you have a talk now.
So I would like to talk about a new project. It's called Minkowski chirality. And it is an ongoing project with some of my co-authors, André Carregea, Kurt Clement Gottwald, Florian Grundbacher, Thomas Jahn, and Mia Runge. This team is quite international. André is from Italy, Kurt is now in Zagreb in Croatia, Florian and Mia is in München, and Thomas is now in Chemnitz. And so the starting point of this was actually a problem from the organic chemistry, which started a long time ago by a famous chemist, Jacobus van 't Hoff, which in 1874 made a famous hypothesis which says that the four bonds of a saturated carbon atom point to the vertices of a tetrahedron. And this hypothesis was not solved for a long time until Einstein's relativity theory. But Jacobus made an observation on some experiments that made him to think that this hypothesis was true. And this was also done with the help of the optical rotation. So in simple words, when the chemistries are talking about molecules, they're making visualization of the molecules as planar connected graphs. Here you have a simple example of two molecules which have the same structure. So it's the same atoms which they are built of, but they're not the same. And to have a better idea about how is this molecule, the shape of it, we need some 3D visualization. This kind was done by the Thomson, which is also called like Lord Kelvin in 1894. And he introduced something that is called chirality. He said, I call any geometrical figure or group of points chiral and say that it has chirality if its image in the planar mirror, ideally realized, cannot be brought to coincide with itself. So the chirality is also found in a lot of elements and also some things that is in nature. For example, here you can see some crystals which are clearly chiral. So this made a starting point for some new section of chemistry, which is called the stereochemistry. And Vladimir Prelog in 1975 got a Nobel Prize for his contribution to understanding these spatial structures of molecules. And also he developed some rules to understanding this molecular chirality. So in general, chirality is really important to have a better idea of the visualizations of molecules. And all my introduction and the motivation was taken by a lecture notes of Vladimir Prelog from his talk from the Nobel Prize. So let's now switch to the mathematical part, which is what actually we can do to contribute to the stereochemistry. And our task is the following. We want to quantify the asymmetry of convex bodies with respect to reflections across subspaces in an optimal containment fashion. So let's break down what this task means and go through it to get a better understanding. So first of all, we need to understand what are convex bodies. So convex bodies mean that are convex, compact, not empty sets. So convexity is a simple meaning that if you have 2 points x and y belonging to your set K, that any combinations, convex combinations of them also belong to this. We also have to restrict our body to be non-empty and compact. The next thing we have to understand what means reflection across subspaces. So let's have here an example. We take a convex body, which is this blue set, which we call here the original set. And we take the 0 point. So let's say that is centered, and let's take as a center its barycenter. Then we can reflect this body with respect to this point. and obtain some rotated convex set. Here we have the reflection with respect to a point. So with respect to the zero-dimensional subspace. We also can consider some other reflection. For example, if we take this vertical reflection line, then the blue convex set can be reflected to the green one. So now we have to understand what means that we want to do it in an optimal containment fashion. This means that we want that this will be not only containment, but in a sense of the best possible containment. Best possible containment of two sets, which is also called the optimal containment, can be seen as such that we have the bodies K and C, such that K is contained in C, and also K is not completely contained in any scalation of C for any smaller factor ρ. This optimal containment can be described by the touching point between those two sets. Okay, and the last thing that we want to understand in our task is what means quantifying the asymmetry. So think about a body. We want to understand how asymmetric is it. So the first one who introduced the concept of asymmetry and quantifying it was Grünbaum in the 1960s, and he introduced the so-called Minkowski asymmetry. The Minkowski asymmetry is an asymmetry where we take the reflection with respect to a point. So here we have the definition. The Minkowski asymmetry of it is just, let's take this away. Okay, here. So this is a minimum factor ρ such that K is contained in ρ times K with a suitable shift. And here you have a picture. So if you have this blue triangle K, then it is contained in minus asymmetry times K, which is this big red triangle. As you see here, we are restricted to the point asymmetry. But as we have also understood from the task of the chemistrist, they're not really interested about the point symmetry, but they're interested about symmetry with respect to some higher dimensional affine subspaces. For this, we need to introduce the chirality, which we call the Minkowski chirality. So the same way as was introduced the Minkowski asymmetry, the chirality, which we denote by lambda j, is the smallest factor ρ, such that K is contained in ρ times the transformed body K with respect to our affine subspace U. We also have the index j here, which is just the dimension of this subspace. So let's have a look at the picture. We have this green body K. Then the gray one is our affine subspace that we use as a reflection line. Then we have K is a reflected body, and then the black one is a scaled one. So we know that for the Minkowski asymmetry, so it's about the point symmetry, we can have the full range of its values. This is quite known from the 1897, which was done by Minkowski. He said that the Minkowski asymmetry has a range from 1 to n, and we also can describe the equality cases. So it is 1 if and only K is point symmetric, and also it is equal to n if and only if K is a full dimensional simplex. So about Minkowski's asymmetry is quite known. So what now about the Minkowski chirality? Can we describe the range of it? What are the extreme cases? We started this checking and we have not found anything in the literature, so we just checked it by ourselves. And this is our results. We have shown that for convex bodies in general dimension D and any index j from 0 to n, The Minkowski chirality lies between 1 and also with a minimum of n and square root of n times the Minkowski asymmetry. So this gives the full range of the values for the Minkowski chirality. Then we would like to know what are the extreme cases. Can we also characterize when we have the equality in the lower bound and in the upper bound? This task was quite tricky, and this is still an open question. So we went to the planar case and we described some special cases. The first special case that we have described is a triangle. So we described that the Minkowski chirality for the triangle lies between 1 and square root of 2. Then we have checked the parallelograms, and we have shown that the Minkowski chirality of it lies also from 1 to square root of 2. Please check that the upper bound for the chirality of the triangles is strict. And the lower bound can be fully described. We have shown that the Minkowski chirality of the triangle is 1, even only if the triangle is isosceral. Also, we made some other observations for the Minkowski chirality, which are connected to the Banach-Mazur distance. So the Banach-Mazur distance is a kind of distance between two convex bodies, which shows how similar they are to each other. And it is defined as a smaller factor lambda, such that taking an affine transformation A, this transformed body L can be sandwiched between K and lambda times K with the suitable translations. For the Minkowski, for the Banach-Mazur distance, it is known that it has some upper bounds. Namely, for general convex sets, the upper bound is n, and for symmetric, so point symmetric bodies, it's square root of n. What we have done is we could connect our Minkowski chirality to the Banach-Mazur distance, which means that if we know what is the Banach-Mazur distance between our body K and the unit ball, then we can bound our Minkowski chirality. Then we went on and we checked about the parallelograms. We would like to completely describe the extreme cases. So we would like to find the parallelograms with the highest value of the chirality. And this was done in this following theorem. We say that K is a parallelogram, and we have that U is a reflection line, which is used for finding the chirality. Then this reflection line has to be one of this following. It could be an angle bisector of the inner angle. It could be a bisector of the diagonals of the parallelogram, or it is the principal axis of the John ellipsoid. The John ellipsoid is the ellipsoid of the maximum volume, which is contained in K. We also could visualize which case appears when, depending on the length of the sides of the parallelogram. The same we have done for the triangle. And it says that if K is a triangle and U is our reflection line, then U must be one of the following. It is either bisector of the largest inner angle, or the bisector of the smallest inner angle, or it should be perpendicular to the longest edge. And the nice part of this theorem is that we could actually even see which case appears when, just by knowing the length of the sides. So here is a diagram where x and y are the side lengths of this triangle. Then the chirality is calculated as a minimum of these three values. And also depending on how large is x and y, we can decide which of the three cases appears. So as said, we have checked the chirality for triangles, for the parallelograms. We also have some bounds in the higher dimensions. And also it would be really interesting to have some more understanding what is happening for example, simplices or some other nice structured three-dimensional cases. But this is still an ongoing project. Thank you.
Thank you very much, Katerina.